Hi, I'm Garrett Wilson, and I'm going to be talking about our paper, Predictive Response Optimization, using reinforcement learning to fight online social network abuse. There's many different types of online social network abuse, and we list some examples here, such as spam, phishing, fake engagement, data scraping, account compromise, and fake accounts. Most prior work on fighting online social network abuse has been focused on the detection problem, detecting abusive accounts. And in this detection problem, there's a trade-off between precision and recall. As precision increases, the recall goes down. As recall increases, the precision goes down. And we illustrate this on the right with this example precision recall curve. However, there's less discussion in the prior work about enforcement actions. What does the service actually do after detection? And what is the resulting user impact? Some online social networks use a mild response for low confidence detections and a harsh response for high confidence detections. Other online social networks use a strike-based system, using a series of escalating actions to give to repeat offenders. The key insight in our paper is expanding the action set. And expanding the action set gives us an additional degree of freedom. So you have the precision and recall, but now you have this additional degree of freedom of what action do you give to which attackers. And so that enables us to push out this Pareto frontier. So we're reframing the problem as action selection, reframing abuse detection as action selection rather than binary classification. And because we've reframed it as action selection, reinforcement learning is a well-known way to select optimal actions. So in this paper, our contributions are this new perspective, selection of enforcement actions as the true goal of online social network anti-abuse systems. And then we also, using this new perspective, add a formalization of action selection as reinforcement learning, where we're balancing abuse volume against the cost of blocking benign users. And to solve this new problem, we design a system called Predictive Response Optimization, or PRO, for this anti-abuse action selection. We implement the system on Instagram and Facebook, and using these experiments, we demonstrate its ability to reduce automated activity volume with no stat-sig impact to users. And then finally, we provide a number of case studies that show its ability to automatically adjust to changing conditions. So let's look at the first part, that new perspective. The traditional rule or strike-based systems have a number of disadvantages. First, abuse prevalence could remain high due to ineffective actions. Maybe the actions are positioned in a way in the rule or strike-based system where they're not optimally given to the right attackers. Second, fixed logic doesn't adapt to changing attacker behavior. Maybe at one point they were in an optimal position, but now over time attackers have adapted to these enforcements and now they're able to get around them. And this fixed logic isn't going to automatically adjust to those changes. And then third, as attackers adapt, maybe you want to add new actions to your system that are more effective. But where do you add them into this rule or strike-based system? And if you add them in the wrong place, that might actually cause metrics to shift in the wrong direction. Maybe it would have been very effective in one place, but it was added in a different place. And so all of this requires a lot of manual tuning and testing to figure out how to optimize this rule or strike-based system. Instead, we propose an alternative, using reinforcement learning to automatically select how to give out these actions. So rather than just classifying entities, we're optimizing a trade-off, where the trade-off is minimizing abuse volume within a budget of operational costs. And so this is illustrated on the figure on the right, where for a baseline method, for example, these rule or strike-based systems, there's going to be a certain amount of abuse volume after the system is in place for a given amount of cost budget. And what we would like to do is reduce that amount of abuse given the same fixed cost budget. And the way we're going to do that is by selecting option or the action enforcement actions to give out more optimally. Now, how do we actually solve this problem? Well, we design a system called Predictive Response Optimization, which combines elements of reinforcement learning with model predictive control. So let's start with the reinforcement learning perspective. Part 1, optimizing actions for each entity. And an entity in this case, you could just think of it as a user account, for example. So for that account, we have a number of actions we could give, actions 1, 2, all the way to N. And we have a number of features for the account, features X, and for each of those candidate actions, let's just start with action 1, for example. We have an abuse model and we have a cost model. The abuse model predicts what would be the amount of abuse if I apply candidate action 1 to this account, and the cost model is similar. What would the cost be if I apply this candidate action 1 to this account? Those give us a predicted amount of abuse, predicted amount of cost, and then our reward in this reinforcement learning system is going to be a weighted trade-off between these two amounts. And we'll get to that, how we calculate that in the next part. But that gives us the predicted reward for candidate action number 1. And now we repeat the same process for action 2 all the way to N. And so we end up with a bunch of different predicted rewards for each of the different actions that we could give to this account. And then on the right here, we select the action with the highest reward. However, we also want to make sure we don't get stuck in a local optima where we keep giving the same account suboptimal actions to an account. And so we include exploration. So we sometimes try out a different action in case that action would actually be more optimal than the current ones we have been giving. That is how we select the action for each entity. But now let's look at where do this abuse and cost metric trade-offs come from? Well, that comes from the model predictive control, the second part, where we optimize the multipliers to enforce global constraints. As the name implies, model predictive control leverages model predictions for our control system. So using the abuse and cost models from the first part, that generates a set of predictions. And we run a simulation over what would the amount of abuse or cost be if we had taken different actions because we had a different trade-off. So this allows us to see for different trade-offs what actions would we have taken and what would have been the amount of abuse and cost given that different trade-off. Using this simulation, we're able to run a constraint optimization problem, finding what is the minimum abuse such that the cost constraints are met. By solving this problem, that gives us the abuse metric trade-off and the cost metric trade-off weights, which we were able to use in the reinforcement learning part. So this enables us to enforce global constraints on those cost metrics. Now that we have designed this predictive response optimization system, we implement it on Instagram and Facebook, 2 social networks, and then apply it to a particular type of abuse problem. You can apply this to other sorts of abuse, but we are evaluating on the problem of data scraping, detecting and blocking bots that were scraping Instagram and Facebook data. And in this context, the abuse metric we use is weighted scraping requests, and the cost metrics are days active on the platform and feedback events given by the users that got enforced. And then we are comparing this with the traditional approach, rule-based action selection, where in our case, we were using multiple classification scores and account information to select those actions. The experimental results demonstrate Pro's ability to reduce abuse volume given this constraints on cost metrics. So on Instagram, we were able to show that it can reduce weighted scraping requests by 59% while no degradation into the 2 cost metrics. Similarly, on Facebook, it was able to reduce weighted scraping requests by 4.5% with no stat sig degradation in the cost metrics. So this demonstrates Pro's ability to reduce abuse volume within those constraints. And now we also want to provide a number of case studies that showcase how it is able to adapt to changing conditions. First, changing business objectives. Over time, you may recognize that you need to introduce different sorts of cost metrics into the system. And here we go over 2 that we were able to introduce. First, days active on mobile web, and by introducing that cost metric, it was able to increase that metric by 68%. And then case study 2, we introduced a new dollars spent on SMS metric, which was able to reduce that metric by 80%. And then next, we also want to introduce new actions into the system over time. And here we introduced a new forced reauthentication action. And this action was able to reduce automated requests by 3% with no statistic change in the cost metric. And then finally, uncontrolled systemic changes. Pro needs to be able to adjust to bugs introduced over time or adversarial adaptation over time. So in case study 4, Pro was able to automatically adjust to a bug introduced into the system. Identity verification action stopped working for some users for a period of time, and Pro responded to that unexpected increase in friction by dropping the selection rate of that action to 0 less than 2 days after the bug was introduced. And then finally, case study 5, adjusting to adversarial adaptation. We introduced a new warning action that showed a reduction in the abuse metric. However, after a month, it was no longer effective. And so Pro responded by dropping that action selection rate from 13% down to 4%. So these case studies have been illustrating how Pro is able to automatically adjust to these changing conditions. So in conclusion, we introduced this new perspective, one of action selection instead of a binary classification problem. And then to formalize that problem, we formalize it as a reinforcement learning problem and develop a new system to solve that problem, predictive response optimization. And then we run a series of experiments that demonstrate Pro's ability to reduce abuse volume within a budget of costs. And then also we provide some case studies illustrating its ability to adapt to changing conditions. Thank you.